Today we're going to look at the first section in Chapter 6. In Chapters 6, 7, and 8, that really makes up the next big portion of the class, and that is all on trig. So I want to first, before we even look at section 6.1, just look at the word trigonometry and see if we can break it down and figure out what these next 3 chapters are going to be all about. So trigonometry. Okay. When we look at the word, does anybody recognize any part of the word that maybe they've seen in another name of a subject, name of a shape, any prefix, suffix, anything in that word that you recognize? Yep.
Try is a 3.
Yeah, so try means 3. Can you give me something in math that has the word try in it?
A triangle?
Triangle, yeah. So triangle, that has try in it. Another name for a triangle is also a trigon, which we actually see that part right here, gon. And what does, anybody know what gon means? When we see that as part of something. Have a guess? Yeah?
Like sides.
Sides, yeah. So we see like hexagon, octagon, pentagon. We don't normally call a triangle a trigon, but you can. Every polygon has a name that ends in gon. So for example, 4-sided shapes we normally call quadrilaterals, but you can also call them tetragons. Okay? Tetragon just means 4-sided shape, and tetra stands for 4. Tetra. Anything else there that is recognizable? Yeah?
And then like the metry, that's like measure.
Yeah, metry. Okay, this means measurement or measure. And we see that in various subjects like trigonometry, geometry. Well, I think that's it. But anyway, you see metry in at least a couple different subjects. So 3-sided measurement, that's literally what trigonometry means. So what we're going to be doing is looking at problems where somehow we can construct a triangle, measure something about it, and that's going to help us to answer our question. In like an abstract way, what we can do is find the lengths of sides and the measure of angles. So when you have a triangle, there's 6 things that you generally have to find if they ask you to find everything that's in it. But what we'll be using the triangle for is usually to solve some type of word problem. All right, so say you had something where you have the ground, and then you've got some kind of structure over here, and you're standing there, and you want to calculate the height of the building. Well, if you can measure a couple things that might be easier than the height, you can use those things to find the height. So if you could figure out how far away you are from the base of the building, and you could figure out the angle when you look towards the top of the building, and there's ways to figure those things out, you have enough information to find the height, assuming the building is perpendicular, okay, built at a 90-degree angle. If the building was leaning, then that complicates it a little bit. Okay, but you basically built a triangle right here. And if you can find the height of it, that's the height of the building. Okay, so that's one example of how you can use trig. Okay, another example would be if you had something where instead of you're just standing at one spot, you have 2 people involved standing in different spots. And let's say that they see something out here. Maybe it's like a fire or something, or they see something, right? But they can see the smoke. These 2 people, if they know how far apart they are from each other, which should be easy to find if they each have some kind of GPS, they can look at their coordinates and figure out how far apart they are. And as long as they can each see where the smoke is coming from, they can what's called triangulate where that position is. But you can't triangulate something by yourself. right? You need two people observing the same thing to be able to triangulate where it is. And the way it would work is if each person has some type of compass or any device that would tell them their direction, they can look at the fire and figure out what the angle is that they look at on a compass to what they're seeing. Now, this person by themselves can only say, well, I can see it in that direction, but they can't tell you how far away it is. They can see smoke in the distance, but they don't know if it's 5 miles, 6 miles, 8 miles. They can't really estimate the distance exactly. But this person can do the same thing. They can say, well, I can see the smoke in this direction. And then knowing the direction each person is looking in and how far apart the two people are, they can triangulate exactly where the smoke is coming from. Right? What's a little harder about that problem is there isn't necessarily a 90-degree angle. So when we do have a 90-degree angle, we have different sides we can refer to as opposite, adjacent, and hypotenuse. When we don't have a 90-degree angle, we can't. So we have to take a different approach to solving something like that. So there's a couple examples of things that you could do with trig. And this second example, that's very useful, especially like somebody that needed to be located using a cell phone. You could think of these two things as cell phone towers. And you could think of the towers being able to ping the person's phone. And the two towers, or even if you have more towers, it's even better. But the two towers working together can ping somebody's phone and figure out exactly where they are. If for whatever reason we needed to locate somebody, there could be lots of reasons why you need to do that. All right, so there's a couple quick things with trig. So before we can even really look at a triangle and solving a problem, we're going to look at what a triangle is made up of, and those are sides and angles. All right, so what is an angle? So when you are defining an angle all by itself, and it's not part of a shape. An angle is made up of two rays that have a starting point in common called the vertex. So here's a vertex. Here's a ray. There's another ray. And now I've just drawn an angle. So that's generally how you sketch an angle when it's by itself. When you sketch an angle inside of a shape, then the angle is usually made up of two line segments, like I did here. Okay. There are no rays in this picture on the left. There's a line segment and another line segment, and that's an angle right there. Okay, so there's a couple ways you can look at angles, either two line segments or two rays. But rays is more common when the angle is drawn all by itself. Okay, each ray has a name to it. One of them is called the initial side. The other one is called the terminal side. And the way that you figure out which one is which is imagine that you're standing between the two rays and you rotate counterclockwise, like this. As you rotate counterclockwise between the two rays, the ray that you start at would be considered the initial side, and the ray that you end at would be the terminal side. Now, technically, when you are between two rays, we can talk about rotation in different directions when we measure angles. But when we are measuring angles in a counterclockwise direction, rotating from the initial to the terminal, that would be considered a positive angle. Okay, so here's an example of a program that can draw different angles. I can't move the initial side. Okay, the initial side always stays right there, but the terminal side I can move. And as I rotate in a counterclockwise direction, notice the angle here increases. Okay. And if we go all the way around, now we have an angle that's even more than, well, we can get an angle that's 360, and then if we keep going, we can get angles more than 360. So we're not really focusing on angles that are more than 360 right now, because I'm trying to explain angles in terms of a triangle. You can't have an angle that big in a triangle that's drawn on a Cartesian coordinate system. If I take the terminal side and start bringing it the other way, it will measure the angle as a negative. Again, when you're dealing with triangles, we don't have negative angles. All right? We'll talk about angles drawn on a circle later on, but for now, I'm just trying to show you a picture of a simple angle. Initial side, terminal side, and the measure is 56 degrees. Okay, there's another picture of initial side and terminal side. Now, technically in that picture, you do have two angles. There's one inside the rays, and then there's one outside. When we talk about the angle, we are generally referring to the angle that's less than 180 when you draw two rays. So for a triangle, you can have an angle that's right up to 180. You can't include 180, but you can go right up to it. It wouldn't be a right triangle, but just kind of an extreme angle like that. That is a triangle. So these two angles can get very, very small, and this one can approach 180, but never reach it. Because all the angles in a triangle have to add up to 180. So any question which side is initial and which side is terminal? Doesn't matter how you rotate it. If you decide to draw your angle like that, this side would be the initial, this side would be the terminal. Think about as you rotate counterclockwise, where you start and where you end. All right, so a lot of times when we are talking about angles, we use a variable to represent them, but we don't use English letters. English letters are usually used for sides. Okay, if you're labeling like a triangle, think about Pythagorean theorem. We use A, B, and C. For angles, we'll use different Greek letters just depending on the context of the problem. Just like in algebra, you might use X, you might use H, you might use F. We use different letters. So I just want to make sure we know what these Greek letters are. So the first one, anybody know what that one is called? Yeah, is that proportional? So I think you're thinking of a symbol like directly proportional. So this is a little different. It's the name of the Greek letter itself. Yep. Yeah, that's the Greek letter alpha. These are also all the lowercase versions of the letters. Okay, alpha. How about the next one? Anybody know that one? Yeah.
Is it beta?
That's beta. And the next one after that, it looks kind of like a Y a little bit. Okay, that one is gamma. Okay, the next one is kind of like the X in algebra. It's the variable that is used most often when you don't know an angle and you're just talking about a single angle. That's the Greek letter we use a lot. Yep.
Oh, that's theta.
That's theta. Yep. And how about that last one? Looks kind of like a W, but it's a little more curved in and it kind of loops on itself in the center. That one? Kind of like the opposite of alpha. Alpha is at the beginning. What? No, not zeta. Good guess. Yep.
You said
What is it?
sigma?
Sigma? No, sigma is a letter we will use later on in chapter 11. We use a capital sigma. We've moved after trig at that point. But that's something different. So that one is omega. Alpha, beta, and gamma, those are generally the labels that we use when we're dealing with a triangle. And we have sides A, B, and C, and angles alpha, beta, and gamma. Omega, you'll see we use that one sometimes later on when we get into graphing trig functions. But that's a little ways down the road. So when you draw an angle, there's different ways that you could sketch it. So that's an angle. But when we draw something, we would generally like our angles to be in what's called standard form. Standard form is when two things happen. First of all, when you draw the angle, the initial side is on the positive x-axis. So it's horizontal and pointing to the right. And the vertex would be at the origin. Okay, so that's an example of an angle that's in standard form. Okay, how about if I did something like this? Is that angle in red still standard form? No, Marcelo, what's wrong with that?
It's too far away.
Can you be more specific?
The vertex is in the origin.
The vertex is not at the origin. Correct. Right. How about if I did something like this? So now the vertex is back at the origin. Okay. Is that standard position for an angle? Yep.
No, because it's not on the positive x-axis.
Right. We've got the terminal side on the positive y-axis, but that's not part of the definition. To be in standard position, initial side has to be on the positive x-axis, and the vertex is at the origin. So what that does is it gives us a way, if I say to sketch a 45-degree angle, everybody's angle would look pretty similar, rather than having them rotated different ways. Okay, so when we measure an angle, one way we can measure it is with what is called degrees. Does anybody know another way that you can measure an angle besides degrees? Yeah?
Radians.
Yes, you can also use radians. Okay, so we'll start out looking at some things in degrees, but eventually radians is going to be the more common way that we use. When you take calculus, if you take that next year, I should say, radians is what is used. They don't really use degrees in calculus. It's all radians. Okay. So now I want to think a little bit more abstractly about an angle. Not just an angle inside of a polygon, but think of an angle like on a circle, like if you were rotating. How many degrees are in one full rotation? And we'll say a counterclockwise rotation. Yeah, Evan?
360.
Yep, there are 360 degrees in one counterclockwise rotation. Okay, the only difference between counterclockwise and clockwise is it controls whether the angle is a positive or a negative. But I think I'm going to write that down in a little bit. How about a half counterclockwise revolution? How many degrees in that? Yep.
180.
Yep, that would be 180. And a quarter revolution? Yep.
90.
Would be 90, yeah. So these are angles that come up quite a bit. In fact, any angle that's a multiple of 30 or 45, we are going to use a lot. And there's lots of things that we're going to have to be able to figure out by hand when the angles are multiples of 30 or 45. Okay, when we're starting to deal with angles that are decimals, or maybe an angle that's not even a decimal, but like 23 degrees, that's not a very common angle, and there's not as much that we would do with that by hand. We'd be using the calculator. Okay, so angles that are measured in a counterclockwise direction, when you're talking about an angle in terms of movement on a circle, are counterclockwise is positive, and clockwise would be negative. And there are generally two main approaches that we do with angles. Sometimes we look at angles as part of a polygon. Sometimes we look at it as an amount of revolution on a circle. Both approaches are similar, but a little different. Okay, so we'll get into those later on. We'll spend a whole section on what's called unit circle trig, where we study movement on a circle. And then later on, we'll get into right triangle trig, which is looking at angles in a right triangle. And we'll also do non-right triangle trig, which is still looking at angles in a triangle, but not having a 90 in it. Kind of like the forest fire problem I showed you. Angles can definitely be larger than 360 degrees. When we're talking about revolutions on a circle, and it just means you've gone around more than once. So the way that this program shows it is that red arc kind of starts to turn into a spiral. That's how it would show you've gone around more than once. And you might have noticed when I get to certain angles, well, there's always two numbers here. There's a top number and then a bottom number. The top number is degrees. The bottom number is, somebody said earlier, that is radians. And all of a sudden, when you get to a certain angle, like 30, it changed a little bit how they wrote it. Okay, they wrote it as a fraction with pi in it. So when we get to converting between degrees and radians, pi is going to be something that comes up quite a bit. You'll notice it again when you get to 45, and again when you get to 60. So angles that are multiples of 30 and 45, there's a lot of special things going on that we use quite a bit. Okay, so the next thing we're going to look at is what are called coterminal angles. So angles are coterminal if they have the same initial and terminal sides. Okay, I'm going to show you a picture of two angles that are coterminal on that program that I use. So there's 90 degrees. And here's an angle that is coterminal with it, 450. 90 and 450 are considered coterminal angles. There are an infinite amount of angles that are coterminal with any given angle. Here's another angle that's coterminal with 90, 810. I could also do something like this, negative 270. That's another angle that's coterminal with all the other ones that I just said. Does anybody see from the pattern that the different angles that I named that were coterminal, how you can mathematically get an angle that is coterminal to something else? Yep.
Add or subtract 360.
Yep. Add or subtract 360 degrees. And the reason that sometimes we work with coterminal angles is when we get into using trig functions, coterminal angles make things easier to figure out. Right? So if I had to take what's called the tangent of 450, I get, and let me do this in degrees. So let me type in the tangent of 450 again. Tangent of, why is it getting mad at me? All right, oh, let's try something smaller. All right, tangent of 350. I get that as an answer. Well, if I take the tangent of 350 and add 360 to it, I'm going to get exactly the same answer, because adding or subtracting 360 gives you something that is what we call coterminal. Coterminal angles will come out exactly the same when we start looking at trig functions. So the advantage is, rather than working with 350, I could subtract 360 from it, and 350 minus 360 is negative 10. So if I don't mind working with a negative angle, I can work with a lot smaller of a number than 350 and still get the same answer. Maybe negative 10 is just easier to work with in my head than 350. All right. So we're not getting into that right now, but that's the advantage of using coterminal angles. We can make an angle bigger or smaller and still get the same result when we plug it into the calculator and start doing trig. All right, so let's sketch. We're going to just practice sketching an angle, and then we're going to find an angle that is coterminal with the angle, one positive coterminal angle and one negative. All right, so let's start with 30 degrees. So in standard position, that means the initial side has to be right there. Where would the terminal side be if I'm sketching an angle that's at about 30 degrees? Yeah, Travis?
Quadrant 1.
Yeah, it would be in quadrant 1. And can you describe roughly where?
A little bit under 45 degrees.
Yeah, a little bit under 45. If you think of the quadrant as a 90 degree, it's about a third of the way through. So, I don't know, maybe something like that. Maybe a little bit lower, but that's okay. So that's about 30 degrees. Now let's find an angle that's coterminal. And positive. What's an angle that's coterminal with 30 degrees and it has to be positive? Preferably the next positive coterminal angle. Don't give me something in like the millions. Yeah.
390.
Yeah, 390. And what would be an angle that is coterminal with 30 degrees, but negative? Yep.
Negative 330.
Negative 330. Yep. There you go. So there's an angle that's coterminal, positive and negative. All right, let's sketch 145. Okay, initial side, no choice about that. Where would the terminal side be? Oh, Lens, where would the terminal side be?
Oh, I forgot what quadrant it was. It's like the second quadrant.
Can you give me direction and I'll tell you if you're right?
It's in the upper left.
Upper left is quadrant 2. Yep. So yeah, it would be in quadrant 2. And can you be a little bit more specific about where in the quadrant?
A little bit past like 135.
Yeah, a little bit past 135. 135 is right in the middle. Okay, so this is the y-axis, this is the x. This angle is a little bit closer to the x-axis. So, something kind of like that. All right, and let's do something that's coterminal and positive. What's an angle that is coterminal to 145 and positive? Yep.
505 degrees.
Yep, just add 360. And to get an angle that's coterminal and negative, we just take 145 minus 360, and we get negative 215. Any questions on that one? Okay. So let's take a look at one more. Okay, negative 45 degrees. There's my initial side. Where would my terminal side be this time? Yep.
The bottom right quadrant, I don't remember.
Bottom right, that is quadrant 4. Yep. And can you be a little more specific about where?
Halfway through.
Right, halfway, right in the middle. Think of it as a line with a slope of -1. Right? Exactly like that. All right. One more time. Coterminal. What's an angle that's coterminal with -45 and positive? Yep.
315.
315. And an angle that's coterminal with -45, but negative. Yeah.
Negative 405.
-405. Good. Okay, given all of those different choices, if we had to work with one of those three angles to do trig, we'd probably choose the 315. We generally like to work with angles that are positive, but between 0 and 360. Most of the time. All right, so now let's talk about how we can classify angles based on their size. What is the definition of an acute angle? Yeah?
An angle less than 90 degrees.
Is there anything less than 90 degrees that would not be considered acute?
A negative.
A negative, yeah. So when we talk about acute angles, they have to be, even 0 is not an acute angle. It has to be bigger than 0 and smaller than 90. So the next one, let's do this one in reverse. What do you call an angle that's exactly 90? Marcel?
Right angle.
Yep, right angle. It's exactly 90. Okay, let's do the other one back to this way. Obtuse angle. What is the definition of an obtuse angle? Yeah?
Above 90 degrees. And less than 360.
It does have to be above 90, but yeah, it has to be less than 180. Okay, so that's how you can classify a single angle. Now, I want to talk about a pair of angles. So complementary applies to two angles, and there's a relationship between them. What does it mean if two angles are complementary? Yep, Raj. Okay, they add up to 90. Are there any angles that would add to 90 and wouldn't be complementary? Right, you can't use negatives. You can't say like -10 and 100. Those are not considered complementary. So it's two acute angles that add up to 90 degrees, or you could say two positive angles that add up to 90 degrees. What's the other kind of angle pair relationship that you usually study when you talk about complementary? Yeah?
Oh, I was going to say supplementary.
Supplementary? And what's that?
They add up to 180.
They add up to 180. Anything else you want to say with that?
Too positive.
Right, they have to be positive. Again, if you had like 200 degrees and -20 degrees. Yep, those do add up to 180, but they're not supplementary. So supplementary has to be positive angles that add up to 180. we already said that. Negative angles do not have complements or supplements. Okay. So I'm going to give you an angle, and I just want you to tell me the complement of it and the supplement. Okay. What's the complement of 48 degrees? Yep.
42.
42. And what about the supplement? 48 degrees.
132.
132. Yep. Okay. How about negative 18? What's the complement of negative 18? Yeah. There isn't any. No. So that doesn't even apply. There's no such thing as a complement. And the supplement of negative 18, well, same thing. Doesn't apply. So now let's think about it in a little bit more general way. What's the complement of x degrees? And you can assume that x is less than 90, because if x was bigger than 90, it wouldn't have a complement. Like if it was 105, it wouldn't have it. So what's the complement of x degrees? Yep.
90 minus x.
90 minus x degrees. So that's a more general formula you can use for finding the complement. As long as x is smaller than 90. If x is bigger than 90, then that wouldn't apply. How about the supplement of x degrees? Yep, mine's
Just be 180 minus 6.
Yep, 180 minus x. Again, for that formula to work, you just have to start with an angle that's less than 180. If your angle is already more than 180, it doesn't have a complement or a supplement. Okay, any questions on that? Okay, so the last thing we're going to look at is an alternate way that we can write an angle besides degrees, okay? Radians. And if you look at the word radian, does anybody recognize another word that's, at least this other word kind of starts with something that's there? Yeah?
Radical.
Okay, radical, that's a good guess, because I do see the RAD. I'm thinking of something else though. I see where you got that. Yeah, radius, right? And when we're talking about radians, it does have to do with a circle, which has a radius. All right, so what I've drawn here is a circle, and inside the circle, I've drawn an angle ACB, where the initial side and the terminal side intersect the circumference, or the perimeter of the circle, is at this point and that point. If you draw an arc connecting those 2 points, that is called an intercepted arc, and the name of the arc is arc AB. Okay, so I'm not going to show you right away how to convert between degrees and radians, but I am going to show you a connection between this arc and something else in the circle. Okay, and it's a connection that we can use as kind of a starting point for figuring out a lot of other things about radians. And that's that this angle right here would come out to exactly 1 radian if the following happens. The length of the arc in red comes out exactly the same as the length of the radius. So that's a special connection between the length of that arc and the size of the radius. If this angle is 1 radian, and you measure that, and then you measure that, they would come out the same. That's not quite to scale. That's a little bit big for 1 radian. because I think you can tell there the arc in red is definitely bigger than the blue segment. But if I brought it in a little bit more, it would be a little bit more accurate. Okay, so that's just something to keep in mind. Anytime you have an angle of 1 radian, the arc and the radius come out exactly the same. Any question on that fact? Okay. So what we want to look at lastly is how you convert between radians and degrees. So there's a formula to do it. It's pretty straightforward. But we've got to kind of figure out the connection. And to figure out the connection, we're going to draw what's called a unit circle. Now, to do this, I could draw a circle of any size. It's just that if I draw a unit circle, it makes what I'm about to do easier to do in your head. And that's because on a unit circle, the radius is 1. That's called a unit circle. Don't have to use a unit circle, again, but it's going to make it easier. And there's something very special that happens in a unit circle. And I'm going to tell you what that special thing is. In a unit circle, if you measure an angle in radians, let me draw an angle, like that. And let me move that 1 so it doesn't look like it's measuring that. 1 unit from there to there. That's the 1. Okay. If you draw an angle like that in a unit circle, and then you measure how big that angle is, and then you measure the length of that arc right here, those two things will come out exactly the same. So if this angle was 1 radian, then this arc would be 1 unit. 1 inch, it depends on what your unit is. If this angle comes out to 2.3 radians, this arc would come out to 2.3 units. 1.6 radians, 1.6 units. These two things are always exactly the same on a unit circle. So what our goal is to find some kind of connection between degrees and radians. So kind of like if I said to you, I want you to convert between feet and inches. As long as I tell you something that's true about feet and inches, anything that's true, you can use that fact to figure out any number of conversions you want between feet and inches. So could somebody give me just what's a fact that connects feet and inches? Any true fact? Yeah?
1 foot is 12 inches.
Sure, 1 foot equals 12 inches. 1 foot, there's 12 inches. So now if you said, well, convert 7.5 feet to inches. Okay. 7.5 feet is how many inches? It all hinged on knowing something that was true. Do I have to use a 1 and a 12? No. We could have said in 2 feet, there's 24 inches. That would have worked just as well here because it would have reduced to 1 over 12. It would have been the same thing. So we need the same kind of thing between radians and degrees. We need our 1 foot equals 12 inches. What's a true fact between radians and degrees? Well, somehow we can use that idea to figure out something that would be true. I want to figure out how many radians in 360 degrees. If I were to draw a 360 degree angle in that circle, how big would the arc be? So that's not a 360 degree angle, and the arc is right there. But what if this angle was 360? How big would the arc be? Yeah. Can you describe it more in words? Try not to use any numbers to describe it. Lens?
It would be just like equal to the circumference.
Right, it would be equal to the circumference. So if we can figure out the circumference of this circle, that's basically the arc that goes all the way around it. And if we know the size of the arc that goes all the way around the circle, that is equal to the angle in radians. So all we have to do is figure out the size of the arc that goes all the way around the circle, and that happens to be the same as the number of radians to go all the way around the circle. And what did you call that? This arc is so big, it goes all the way around. You called it it's the circumference. So what we have to do is figure out the circumference of that circle. And whatever it comes out to, that is the size of the angle measured in radians that goes all the way around the circle. So what's the formula for the circumference of a circle? Yeah?
2 pi r.
2 pi r. Circumference is 2 pi r. What's the radius on our unit circle? Yeah? 1. So the circumference is 2 pi times 1. The circumference of that circle is 2 pi units. That's this number, 2 pi. But the length of the arc is equal to the measure of the angle in radians. So if the circumference is 2 pi, then what's the measure of the angle that goes all the way around the circle? Yep.
360
360 what?
degrees.
Okay, this statement right here doesn't tell us anything about degrees. Yep.
2 pi.
2 pi, yeah. We know the length of the arc in our problem is 2 pi. So the radian measure of the angle is equal to 2 pi. That's the length of our arc. Right? So if we look at our diagram and we go all the way around the circle, notice what it says. 360 degrees is 2 pi radians. So now we have a connection between degrees and radians, just like 1 foot equals 12 inches. We can use that connection to figure out anything we want to know to convert between degrees and radians. So 1 full revolution on a circle, we already knew it was 360 degrees, but what we know now is it's 2 pi radians. Well, if 1 revolution is 2 pi radians, then we can reduce that and say that a half of a revolution is 1 pi radian, just a reduced version of that. So now let's say that usually when you give someone a conversion, it has a 1 in it. Like if you're going to tell me how many feet in an inch, or how many inches in a foot, you'd probably say 1 foot equals 12 inches. You could say 5 feet equals 60 inches, but you're giving it to me in a more complicated way. Why don't you just tell me in one of it, how many are there? Okay. So let's get a 1 on one side of this equation. let's say that I want to get a 1 on the, let me just match this up with what we're going to do. Let's get a 1 on the right. How would I get a 1 on this side? Yep.
Divide both sides by 180.
Yeah, divide by 180. Now you've got a formula for 1 degree. 1 degree is pi over 180 radians. Let's say that I wanted a formula for 2 degrees. What could I do with this equation now to make it say 2 degrees equals, and then something on the other side? Yep.
2 pi over 180, right?
And so what can you do to both sides of your equation?
Multiply by 2.
Yeah, multiply by 2. Multiply by 2. Multiply by 2. Now you've got a formula for 2 degrees. What if you wanted a formula for 5 degrees? What would you do? Yeah.
Multiply both sides by 5.
You'd multiply both sides by 5. What's in the red box isn't what's important. This is the conversion that's important. If you're trying to convert degrees to radians, you multiply what you're trying to convert by pi, and you divide by 180. Those are the 2 steps to convert from a degree to a radian. So if you want to convert 8 degrees to radians, you multiply it by pi, that would be in the top, and you would divide it by 180. 8 pi over 180. And sometimes in that case, you end up with a fraction you can reduce. So we always reduce it as much as we can. Okay, now let's get a 1 on this side. What would you divide both sides by if you wanted to make a 1 on the left? Yep. Divide by pi. So you have 1 radian equals 180 over pi degrees. That's dividing both sides by pi. So now if you want a formula for 2 radians, multiply by 2, multiply by 2. If you want a formula for 7 radians, because you have to convert 7 radians to degrees, multiply by 7, multiply by 7. It doesn't matter what you're multiplying by. This is the conversion. Anytime you want to convert from a radian to a degree, you would multiply what you're trying to convert by 180, and you would divide by pi. Okay, so let me show you an example. It says convert 30 degrees to radians. Degrees to radians. Multiply by pi and divide by 180. What's going to happen to the degree symbol there? Yeah?
It'll cancel out.
It cancels out. Degree symbol cancels out, and you're left with, if you reduce that, partially reduced, you get 3 pi over 18. Or when you fully reduce, how many times does 3 go into 18? Yep, 6. And that's how you write 30 degrees in radians. You do have to get used to not seeing RAD. Okay? They don't write RAD on it. We know that when we're talking about angles, if it doesn't have a label on it, it's radians. If you want it to be something other than radians, then you need to put the little circle for degrees. But the little circle is that's the only label that you ever put. Okay, let's do this one. Convert degrees to radians. Multiply by pi over 180. Degrees cancels. And how many times does 45 go into 180? How many, Vanessa? 4 times. So it's pi over 4. Okay, 60 degrees would be the same thing. Multiply by pi over 180 and just reduce it. How many times does 60 go into 180? Marcelo? 3. Pi over 3. If they ever ask you to round 2 decimal places, you can. Just type this in on the calculator. Don't use 3.14. Use your pi button. It's more accurate. Always use the pi button. Okay, and let's finish up with converting 1 the other way. Convert 2 degrees. When you're converting 2 degrees, you multiply by 180 and you divide by pi. What cancels out there? Raj? The pi. And how many times does 2 go into 180? Yep. 90. So you end up with 270 degrees. Okay. Any questions on that? All right. So that was pretty much it. We're not doing that tonight. So again, tonight will be the take home. Is there anybody that doesn't want to do the test as a take home and rather do it in class? Okay, so I'm going to verbally go through what's going to happen, and then I'll write it all on the board when you guys are done. The test will open at 2:40 today. It will close at 8 a.m. tomorrow morning. If it's late, it will be a 0. You will be able to have 100. I'm going to give you 100 minutes. So that's more than a normal test, and this is shorter because there's not as much material. So you'll have 100 minutes. And again, if it's late, it would be a 0. Any questions on that? And it's due 8 a.m. tomorrow morning. That's when it's going to close. You will not need a password for it on Schoology. It'll be open, and you can use your notebook, textbook. Okay. All those resources are fine to use.